So next we do the example of the common base. Okay, so we'll do the analysis for some important or the main parameters, which is input and output impedance, voltage gain, and current gain, power gain. Okay, so this is common emitter. So the VA is given as infinity. So this is R0 is infinity. And IC is 2.37 milliampere. So this from the IC we can calculate the GM is IC over 26 milli. So this is 2.37 milli over 26 milli. So this is equal to 91.15 millisiemens. For when we know the GM, we can calculate the R pi. R pi is beta over GM. Beta is 120 over GM is 91.15 milli. So this is equal to 1.32 kilo ohm. So okay, you know all the answer, so all the parameters in the mid-band equivalent circuit. Next, you need to draw the mid-band equivalent circuit. Okay, when you draw the mid-band equivalent circuit, we start from the VS here. So we'll have here VS. This is VS, and then VS is connected to the RS, which is 600. Okay, VS, and then we have the RE connected to the ground. Oh, sorry. Okay, the RE connected to the ground. Okay, this is the emitter point. Okay, and then see here, this is the base R pi here, the base point. Okay, the base point. This is at the base point. So at the base point, the C3 will bypass. Will have the bypass. This is bypass capacitor and bypassing to the ground. So the R2 and R1 will not appear. Okay, for R1 because PCC is ground, so this is ground, R1 also disappear. So the terminal for base, so this is base, will be connected to the ground. And then we have here, this is GMV pi. Okay, at the collector we have the RC, and then at the output port we have the RL. Okay, this is collector port. Okay, next you can also draw the current direction, because this might be useful for you for the next analysis. For the base current, this is towards upward. So the V pi polarity will become like this, and the emitter current is towards right hand side. So this is IE. Okay, so we can calculate the Z-in. So Z-in is seen from the input port. So Z-in is equal to RE parallel with ZB. ZE. So what is ZE? ZE is the impedance seen from the emitter port. Impedance seen from the emitter port. So this is ZE. Okay, for the ZE, we see the ZE is equal to voltage at the emitter here. So voltage at the emitter here is the voltage drop at the R pi. Okay, if I use the base current here, so the voltage at the R pi is negative IB. R pi is 1.32 K. Okay, so this is the voltage of the voltage drop at the R pi. equal to voltage E at the emitter. Okay, for this ZE calculation, we need to consider the current entering the emitter port. So the current entering the emitter port is actually equal to minus IE. Okay, and then the minus IE, you can convert it to replace it with the beta by multiplying with the beta plus 1. So this one is IB 1.32K, and then this is minus IB beta plus 1. Beta is 120. So you can cancel out this one. As lastly ZE, you will get 10.9 ohm. Okay, and then the ZI will become RE is equal to 1K. RE is 1K. So 1K parallel with 10.9 ohm. So this calculation will give you the input impedance equal to 10.78 ohm. So it's very low. It's quite low input impedance. Okay, for the output impedance, is seen from the output port. This is Z out. So the Z out is equal to RC. RC is equal to 4.3K. This is Z out. Okay, next we calculate the AV. So what is AV? AV is V out over V in. So the V in is here. This is V in. V out is voltage across the RL. Okay, so the equation for V out is equal to the voltage drop at the combination of RL and RC. So we use the Ohm's law. So the current across the combination of RC and RL is negative GMV pi. So negative GMV pi times RC parallel with RL. So this is negative 91.115 milli, and then we have the V pi. RC is 4.3K parallel with 10K. So here you will get the RC parallel with RL is equal to 3K. So the equation is, the answer is 273.45 V pi. So this is the V out. Okay, how about the V in? So the V in here equal to the voltage at the emitter, and the voltage at emitter is equal to negative V pi. Okay, and then from this calculation, the AV is negative 273.45 V pi over negative V pi. So you got this one is 273.45. So this is AV. Okay. So you can calculate from the AV. You can also calculate the AVS. The AVS is V out here over Vs. So this is can be rearranged to V out over V in times V in over Vs. Sorry, Vs. And then V out over V in is equal to AV. So next, you need to get the what is V in over Vs. Okay. From the voltage divider, V in is equal to Z in plus Rs Vs. So you got here the V in over Vs is equal to, the Z in is quite low. This is 10.78. 10.78 over 10.78 plus 600, so this is 0.018. So lastly, the AVS is equal to AV times 0.018. AV is 273.45. So the answer is 4.92. So this is AVS. Okay, you can next we calculate what is AI. So now we define the AI as the IL over II. So IL is the current flow across the load. This is IL. II is the current at the input port. This is II. Okay. So for this, the IL, you need to define what is IL. So IL, you can get the value of IL from the current division between RL and RC. Okay. Current from the current source is negative GMV pi. So the IL will be RC over RC plus RL negative GMV pi. So this is RC is 4.3K, 4.3K plus 10K. GM is 91.15 milli V pi. Oh, sorry. Let me rewrite this one. So this is 91.15 milli V pi. Okay, from this equation, you will get the IL is equal to negative 27.41 milli. This is V pi. This is IL. How about the II? Okay, for the II, you can use the input impedance. II equal to VI over ZI. Okay, you know the VI is equal to negative V pi, and then the ZI is equal to 10.78. So from this II and IL, you get the AI. So you can get the AI is equal to this IL over II. So the AI is when you divide this, the minus sign will be cancelled out, as well as the V pi is also cancelled out. So you will get 27.41 milli times 10.78. So this is the answer is 295.5 milli. So it's very small. So it's around 0.29. Okay. So last one, calculate the AP power gain. AP is AV times AI. So AV, we have calculated the AV is equal to 273.45, and then AI is 295.5 milli, or equal to 0.2955. Okay, so now you get the AP is equal to 273.45 times 0.2955. Okay, this will get you around 80 something. Let me confirm this one, the calculation. 80.8. We get this one is 80.8. So this is the answer. Okay. This is the last slide. The last slide summarize the characteristic, the comparison between the common emitter, common collector, and common base. For the common collector, the voltage gain is very large. So it means that if you want to use, you want to have the large voltage gain, you might consider the common emitter or common base. But common emitter will have 180 phase shift, means that the output signal is inverted. Okay, for the current gain, the common emitter and common collector offer a large current gain. They provide a large current gain. So in total, in terms of power, the common emitter is better because it will give more power gain. Okay. But in terms of the input impedance, in the voltage amplifier, so we prefer to have the high input impedance. So in this consideration, maybe the common collector is more suitable. And for the output impedance, you need to have the low. You need to have low output impedance. So common collector is also better. But the problem is common collector, the voltage gain is less than 1. So it's not amplifying the voltage.